Okay, so this is the lecture 7, transmission lines part 2. We'll be continuing from the transmission lines part 1 we did in the last lesson. So we're going to introduce a new term called reflection coefficient. Now, each interface, when you have two different impedances, as in this case here, so there's the impedance is at load presented to the wave that's coming towards the load. The impedance of the transmission line is at 0 and the load impedance is at load. Now, so we can write the voltage at an Z distance, at a Z point, which is here, and in the form of V naught plus E minus J beta Z plus V naught minus E J beta Z. The current, we can write it as the voltage divided by the impedance at this point, and it comes in the form as that. So this is the forward current, the reflected current, forward current, reverse current. Now the length Z is actually measured from this interface. So if Z is 0, that means you are here. If Z is, say, L, certain distance, you are here. So depending on what you put for Z, you can calculate the voltage and currents. If you know V naught plus, V naught minus, I naught plus, I naught minus. Now we are interested here at this interface, where there is the impedance difference between the side on the left and side on the right. So what we have to do is, at Z equals 0, we need to find the V naught or I naught. So because V naught or I naught gives us the impedance. So we're trying to look at the impedance, what happens to the V naught or I naught at this point, which should be equal to Z load, because that's the impedance at this point. So if I sub in Z equals 0, then you will end up with this formula. V0, Y0 is Z load, and then Z0 coming from this one from the denominator, and then we get V naught plus, V naught minus, because this all get to 1. So all get to 1. That's 1 because it's 1. So you end up with an equation like that. Now you can rearrange this term. So simply, if you take this term, you can rearrange it so that you can get V naught minus over V naught plus. So this is the ratio between the reflected wave voltage and the incident wave voltage. And we call this the voltage reflection coefficient, which is tau V. So if you rearrange this, you do the algebra, you will end up with something similar to this. So this is something you need to remember. So this is a voltage reflection coefficient tau V equals to the load impedance divided by the source impedance. So the impedance left to that interface. And then it's at load plus is at 0. Right? So we can look at this a little bit in detail now. So what happens if Z load equals Z 0? So in that case, tau V becomes 0, because this Z load becomes 0, and this doesn't matter, it's 0 divided by something. So that means reflection, voltage reflection towards the source is 0. So the reflection coefficient, the voltage reflection coefficient, gives an idea how much reflection there is towards the source. So depending on the load chosen and the source impedance, you get a certain reflection. Now, if they're equal, so if they're equal, you can think this is actually a continuation of the transmission line, because it's the same impedance. Now, say if it is Z load equals 2 Z naught, and the tau reflection voltage would be 2 Z naught minus Z naught divided by 2 Z0 plus Z0. So that's going to be Z0 by 3 Z0. It's 1/3. That means 1/3 of the voltage that comes into the interface. The reflected voltage amplitude is 1/3 of the incident voltage. That's what it means. So you get 1/3 of the voltage value sort of reflected towards the source. Now, if you want to transmit a signal, the idea is you want to transmit the power without a reflection, so you can deliver the full power to the source. Now, we'll look into the power in a couple of slides, but the idea behind defining a reflection coefficient voltage, tau V, is to assess the reflections at any interface if you know the impedances on the left and right hand side of that interface. So that's so you can also, now once you know V0 minus V0 plus, you can sub that in here and then rearrange, and you can get this formula where if you know the impedance of the on the left hand side, that's the source, and then when you know the reflection coefficients, you can work out, because you can measure the reflection coefficient. And then once you know that, because you know the impedance of the transmission line, you can work out what would be the impedance of the load. So that's another way of deriving load impedance if you know the reflection coefficients. So we'll do an example. A load consists of a shunt connection of a capacitor 10 picofarad and a resistor 60 ohm. The load terminates a lossless 50 ohm transmission line. So it simply says that, so you have a transmission line, that's Z0 is 50 ohm. This is the place where my screen is not very sensitive. Z0 equals 50 ohm. The load terminates a lossless 50 ohm transmission. The operating frequency is 5 GHz. So F is 5 GHz. So shunt connection, that means there's a cap 10 picofarad and there's a resistor 60 ohm. So the part A is asking what is the impedance of the load. So the load impedance ZL represent this whole thing. What would be the load impedance? So it's actually R parallel C circuit. So that means R, so parallel C circuit. So if you think this was Z1, Z2, what you need to get is 1 over Z2, because they are parallel. That's the answer, right? So Z1 in this case is R, because it's a resistor. Z2 in this case is 1 over J omega C. So J 2 pi F is 5 10 to the power 9. Capacitor is 10 picofarads, so that's 10 to the power minus 12. And then you can find Z2, and you know R is 60 ohms. Then you can sub in those values, and then you get Z load. So when you find the values, you get Z load around 0.168 minus 3.174 J. So it's not just a resistive, because it has it's not a resistive, only it has a imaginary part to it. Now that's part A. So we have to do part B. What is the normalized impedance of the load? So normalized impedance, when we define normalized impedance, it's basically Z normalized equals the load impedance, or whatever the impedance divided by Z0. That's normally a 50 ohm. So we tend to talk all the systems in terms of 50 ohms. We try to normalize them into 50 ohms. So divide Z load by that, and you will end up with the value 3.36 to the power minus 3 minus 0.063 J. So what is the reflection coefficient of the load? So you need to find the reflection coefficient. part C. So when they say reflection coefficient, they didn't say it's a voltage reflection coefficient or the current reflection coefficient. There are two reflection coefficients that I forgot to mention in the previous slide. So this is the voltage reflection coefficient. You can also find the current reflection coefficient, where you can define reflection coefficient of current is I minus divided by I plus. Now what you will find is, once you do that, is current reflection coefficient is negative of voltage reflection coefficient. So it just has a reversed sign. So what is the reflection of the load? So if they don't mention anything, it's talking about voltage reflection coefficient. So reflection coefficient is Z load minus Z0 divided by Z load plus Z0. Now you already found the Z load and Z0, so you can sub in those values. Now because it's normalized already, you can just use the normalized value. If you haven't normalized it, you could use this value, but then Z naught is 50 ohms. Now what I meant is, so if you use 0.168 values, 31174J, that's not normalized, so you have to minus 50 and then do the same plus 50. If you use the normalized values, you get 3.36 10 to the power minus 3 blah blah minus 1 divided by the same value plus 1. That's what you need to do, and you'll find the answer as minus 0.985 minus J.126. So okay, so that's part C. Part D is what is the current reflection. So this is the current reflection coefficient, which is the negative of voltage reflection coefficient. So whatever this value, the negative of that. Now we were talking in terms of power reflections. No, sorry, current voltage reflection and current reflection. What's more important is about the amount of power that is reflected at an interface. So we try to find out the power reflected or power flow and return loss, define few parameters around that. So at an interface, if you look at that, so you same as you were thinking about voltage incident and voltage reflected, we can also define power incident and power reflected. So power incident can be defined as the half. Now this half comes from, so normally the power is defined as VI, right? It's again same area in the screen. Power is defined as VI. Now because we talked about the voltage, the peak voltage, because we're talking about peak voltage, when you look at, this is V naught, I naught. When you talked about, when you find the power plus or whatever, doesn't matter, you have to, so the voltage and the current can be complex numbers. So you have to look at the real part of it. So you basically get voltage and the current. Normally, this is about resistive systems. If you talk about power equals VI, but when you have complex voltage and currents, the power flow that is delivered in the forward wave is given by this equation. That's pretty much half the real part of voltage and current conjugate. Now we don't want to derive this, but you don't even need to remember this. You just have to actually you have to remember this. This is not our real part of this. The derivation of it is not something that you need to remember, but at the end of the day, the result of that is P plus is, in terms of voltages, half the maximum voltage it can see, which is V naught C squared divided by Z naught. And that's the magnitude of it. So if you sub in the P plus and you get the same way the P minus, so P minus will have V naught 0 minus, but then you can, because you know that tau is V naught minus or V naught plus, you can sub in V naught minus. Instead of V naught minus, we can sub in, from here we can say V naught plus tau is V naught minus, so you can sub in that here. And then you get this for P minus, and then you have P plus, you sub in. So this power load is the power difference between P plus and minus. So if it's in watts, P plus minus P minus is a volt power difference, and that's the power that's delivered to the load. So the PL equals P plus minus P minus. And then you can, if you sub in these values, you'll get this formula. That's the power delivered in the forward wave times 1 minus reflection coefficient squared. Now this is something important, remember, even though if you don't remember how to derive it. And then you also need to remember this tau is the reflection coefficient. We tend to deal with them in terms of logs. So we can take the log 20 of that tau reflection coefficient, and that's what we call the return loss. Now the idea that we need to take home from here is that return loss is a measure of how much of the available power is not delivered to the load. That means it's, so I want to stress that it's not delivered to the load. So how much power is reflected is what return loss is measuring. So smaller it is, better, because you are delivering almost all of your power to the load. So we want to make sure in a system like in amplifiers that you are designing, the return loss is as minimum as possible. So because it's a loss, it's a positive term. That's why, to make it positive, that's why you have the negative value here. Now, assuming that you have a reflection coefficient of 0, right? So that means voltage reflection coefficient of 0, V minus over V plus. What does that mean? That means the V minus is 0. That's the reflected voltage is 0. That means almost all the power is delivered to the load. So if you put 0 here, log 0 is infinity, minus infinity, and then you get the infinity for return loss, right? So that means if you have a return loss of infinity dB, that implies that you don't have any reflection from the load. So this is very similar to the S11 curve. So S1 is actually the negative of return loss, negative value of return loss. So normally, if you have this axis as a frequency, S11, we want that to be normally minus 10. So minus infinity. So I just want to imply that S11 is minus return loss. So if you want to just plot return loss, let's plot return loss without going to S1, because we'll be covering S1 and S22 separately. Return loss, if it's infinity, that means no reflection at all, right? So normally we do have spec of 10 dB or more is good enough that we have very small amount of power reflected. So what happens if you have 10 dB here, return loss of 10 dB? What does that mean? So 10 equals minus 20 log reflection coefficient. So minus half log reflection coefficient. So reflection coefficient is 10 to the power minus 0.5. So that means that means 0.31. That means the answer is reflection coefficient is 0.31. 3, 1. So that's only the 30% of the voltage is reflected back when you have an input power as 1. So out of that 0.3 of the voltage is returned back. We think that's sufficient. Most of the systems, that's the voltage in terms of voltage. So that's what it means. So as long as you have a return, if the return loss is a larger value, that's good because you have less reflections. Now what happens if tau is 1? So if log 1 means reflected wave V minus or V plus equals 1 means V minus and V plus is equal. That means total voltage, the reflected wave is equal to the incident wave voltage. So that gives you 20 log 1, which is 0. So return loss of 0 dB is not good because that means all the power is reflected back and you don't want that. Okay, let's go through this example. The transmission line shown in figure 416 consists of a source with Thevenin's impedance Z1 of 40 ohm and the source is 5 volt peak to peak. So that's 5 volt is peak voltage. Connected to a quarter wavelength long line of characteristic impedance Z01 40 ohm. So that this is 40 ohm and this is also 40 ohm, which in turn is connected to an infinitely long line of characteristic impedance. So this is long, that means this is pretty much just a load. And then Z02 is 100 ohms. The transmission lines are lossless. Two reference planes are shown in figure 416. At reference plane 1, the incident power is PI1, the maximum available power from the source. The reflected power is PR1. And the transmitted power is PT1. So that's transmitted power, reflected power. So this is in terms of power, incident power. At the interface 1, the maximum available PI2 is the maximum available power from Z01. Okay, PI2 is that. PR2 and P2 are similar quantities at reference planes 2. Okay, are steady state quantity. That means it's already steady state means it's not changing. So when you connect the source, usually it sort of try to, it'll have a spike and then it'll settle down. So question is asking what is PI1? Okay, so PI1. The part A. So we have a 5 volt peak to peak source. So we have a voltage source, 5 volt peak to peak, and then we have 40 ohm. Right, for this interface 1, then we have a 40 ohm load from Z01, that's Z01. Now for the maximum power transfer, so well, we don't need to talk about maximum power transfer. We have 40 ohm, and if this is 5 volt peak to peak, the voltage across that is divided half because it's the same voltage. So that's going to be 2.5 volt peak to peak. So the power, as we talked about before, half V squared over impedance. The half comes because the voltage is peak to peak voltage. If it's square root, if it's RMS, then this you don't need to have that. So V squared is 2.5 volt squared, half divided by impedance of 40 ohms. In this case, it's real. So once you solve that, you'll get about 78 point. So this is in watts. You get 78.13 milliwatts. So that means this load here consumes has incident power of 78.13 volt, 13 millivolts. So that's PI1 equals 78.13 millivolt. So then you have a PR reflected one, and then you have P transmitted one power, right? Okay, so what is the PR1 at this interface? Because it's this 40 ohm here, and that's 40 ohm here. So what happens is the reflection coefficient, if you look at that, tau V is Z load minus Z naught over Z load plus Z naught. Because the volt impedances are same, there's no reflection. So that's good. That means all the power gets transmitted through. So the PT1 is also 78.13 millivolt, and that's 0 millivolt. Okay, because we need that for the second part. So what is the second part asking? It's PT2, the transmitted power to the 100 ohm load. Now at this interface, we need to find tau V. Okay, so if we find tau V, I'll do it over here. At the second interface, is Z load minus Z naught over Z load plus Z naught. Now for the second interface, Z load is 100 ohms, and this Z0 is 40 ohms. Therefore 100 minus 40, 100 plus 40, you get 60 over 140. Yeah, that comes about 0.428. So we know the reflected power. So then what we can do, the other thing is we can look at the P. So at the second interface here, this interface 2, so you have P incident 1 and then P incident 2, reflect 2. So you can look at the P reflected 2 over P incident 2, and that's same as half V incident V reflected 2 divided by whatever I said, half V incident square divided by 2. And then when you cancel that out, you get VR squared over VI squared, and that's tau squared. So we can find P reflected in terms of incident power, because incident power you already know, and tau squared. So tau squared times PI2, because PI2 is the same as PI2, the P transmitted one will go as the PI2. So here PT1 equals PI2. So we can say tau is already 0.428 squared times, instead of PI2 I can say PT1, and then once you do that, 0.428 squared PT1 is 78.13 milliwatt, and you get an answer in milliwatts. That's about 14.3 milliwatt. So you know the P incident 2, and then you know P reflected 2. Then you want to find P transmitted 2. Yeah, PT2. So you know this is 78.13 milliwatt, and that's reflected 14.3 milliwatt. So whatever the difference gets through here, which is 78.13 milliwatt minus 14.3 milliwatt. That comes to 63.8 milliwatt. Okay, so that's the answer for the part B. Now in this next example, the transmission line is driven by a generator with a maximum available power of 20 dBm and a Thevenin equivalent impedance of 50 ohm. The transmission line has a characteristic impedance of 50 ohm. What is the Thevenin equivalent generator voltage? So it's very similar to the previous one. So we have a voltage source of V1 because it's a Thevenin equivalent, and then we have 50 ohm characteristic impedance in the transmission line. The transmission line is the characteristic impedance 50 ohm here. 50 ohm is the source impedance as well. So this is say V source, and then we say it's V1. That's V1 here. And it has the maximum available power. So the power dissipated here, or power delivered to that, is P is 20 dBm. Now you haven't seen the dBm before. So dBm is usually we tend to, you may not have seen that we tend to measure things in terms of dBs because it's easier. Otherwise, linear scaling is difficult to represent larger numbers. So the P, if it's in dBm, you can represent. So dBm pretty much says power in dBm is 10 log of something. So if this is the power that you're going to represent in watts, so in dBm means it's compared to 1 milliwatt. So basically, if you convert P1 to milliwatts, say it's whatever the power P1 in milliwatts, with respect to 1 milliwatt, and then you get 10 log of that value, you get the power value in dBm. So in this case, it's 20 dBm. So if you want to find the power log P1, you get 2, 10 to the power 2 equals P1. That means P1 is 100 milliwatts. So the units are in milliwatts here because that's why it gets cancelled. This is something important to remember to convert the power from a milliwatt to the power in dBm. So now we got the 100 milliwatt at this point. So we know that the power transmitted to that equals half voltage peak to peak divided by the impedance of that load. So half 100 squared, because I am doing it in, this voltage. Half voltage across that's V1, impedance of 50 equals 100 milliwatts. So it's 0.1 watt because you need to have it in standard units. So that will come to, when you calculate V1, that will come to 2, 5, 10 equals 3.16 volt roughly. So that's the voltage across this resistor. That's 50 ohms, and this has a 3.16. So therefore the V source has to be 2 times 3.16 volt, which is 32, 6.32 volt. Okay, so what's the Thevenin equivalent generator voltage? That's the answer for part A. What is the magnitude of the forward traveling voltage wave on the line? So it's already we calculated that 3.16 volts. So part B is 3.16 volt. Assume the line is infinite long here. Part C, what is the power of the forward traveling voltage? The power when they ask in terms of dBm, it's already given. So the part B answer is quite straightforward, even if you So C you can still say, because without even calculating, because it's the same impedances 50-50, so your reflection coefficients is 0, therefore full power is delivered to the transmission line. So now we come to calculating, so translating an impedance. So we previously talked about an interface, and then we looked at the impedance at that point. Based on that, we calculated the reflection coefficient. Now, how do we tell an impedance at a certain distance L from the load if we know the impedance of the transmission line? Because we are interested in looking at the impedance at the source. If you think this is a source, and if you know the load impedance, we are trying to find out source impedance based on the load impedance if you know the characteristics of the transmission line, which is Z0 and beta. So this is given by this lossless telegraph equation, which is this. Now you can, if it's not hard to remember this, but even if you don't remember, but this is an important equation. So if you have a short note of all the important equations, this is one of them for your exam. Now we can look at L equals 0. That means if you are here, what happens is that L equals 0, tan beta L equals 0. So that means this whole term goes to 0, tan beta L is 0. This whole term goes to 0. That means this whole term 0, 0. So you're left with Zin equals ZO times Z load over ZO. Cancels out. So input impedance at this point is Z load. So that's something we already know. Now let's look at another case. Now beta, if you remember, beta equals 2 pi over lambda from the previous lecture. Then the loss in the lossless line when alpha is 0. So let's look at L, because the lambda by 4 case. So if L, so let's look at lambda by 2 because it's easier. So your beta L product is 2 pi over lambda times lambda by 2. So you get tan pi. Tan 0, tan pi is 0. So this is all 0 again 0. And then your input impedance again becomes Z0, Z load over Z naught. Then input impedance at L of lambda by 2, you're back to the same impedance as Z load. So here, if the length is lambda by 2, input impedance here is Z load again. So that's interesting. So in between, say lambda by 4, what happens? So beta L, maybe I'll just clean it up a little bit. Now what happens if it's lambda by 4? So beta L becomes 2 pi over lambda by 4. So it's pi by 2. So tan pi by 2 is infinity. So if you want to solve this, you have to get the tan beta L product outside. Divide top and bottom by tan beta L. So you're left with Z load divided by tan beta L. J Z naught. Z load Z naught divided by tan beta L. J Z L. So this goes to 0. This goes to 0. That cancels out. So left with Z naught times Z naught times J divided by Z load times J. Cancels out. So your input impedance is Z naught squared over Z load. Okay, so this is something you need to remember. We'll come to that. So it's not either Z load or it's not zero. It's something else. So you basically, as you travel along the line, your impedance change, but it comes back to the original impedance after half wavelength. Yeah, we can look at certain special cases. Now assume if Z load, so assume this end is Z load, this end is open. So if it's open, impedance at an open interface is infinite, right? So now if I rearrange this, Z in, Z load, so I'm just rewriting the equation. Now I'm going to make this Z load infinity. So if I take Z load out, 1 plus j Z naught over Z L tan beta L 1 plus Z naught over Z L plus j tan beta L. So this goes to 0 because Z load is 0, infinity. And that goes to 0. So I'm left with Z naught divided by j tan beta L. Now if I want to get j to the top, I times it by j, so you get minus j Z naught tan beta L. Okay, so now that means, so that's pretty much this. In the same way you can actually, okay, so we'll come to that later. But this is Z1 in open circuit stuff. Now the special case here is when when L, length of that line, if this length of that line, L here, is lambda by 4, what happens is beta L becomes 2 pi by lambda times lambda by 4. So you get pi by 2, and tan 90 is infinity. The whole term is 0. So Z1 equals 0 when L equals lambda by 4. So that means quarter wavelength from here to here, this is seen as 0. So you can transform an open circuit line to a short circuit by making sure the length is lambda by 4. So it will work for a particular frequency, because for that frequency, so around that frequencies, so this point here, it will think it sees this as a short circuit, although this end is open circuit. The same way, you can also derive this. If it's short circuit here, if you select the line length lambda by 4, you will see an open circuit, infinite impedance here. So you can always transform a short circuit to open circuit, or open circuit to a short circuit by using a lambda by 4 length. So for example, if you have a transmission line and you get a length lambda by 4 line from that, then short it and this becomes open. So it doesn't see any effect because of that. If you short it here and this length is lambda by 4, at that particular frequency, this point is open. So this transmission line is at say source and they said load. They don't see this effect. But if you keep this open and lambda by 4 at that particular frequency, this becomes short. So you said source will not see the load because it's all shorted here. So it only sees a line that's shorted at this point. So that's the importance of that. So you can You can short or load, short or open certain points. If you pick, you call the stub lambda by 4. So this example, a shorted coaxial line is used as a resonator. The first resonance is determined to be a parallel or shunt resonance and is at 1 GHz. Draw the lumped element equivalent circuit of the resonator. So it's a parallel resonator. Parallel resonator is where you have, so it's as a lumped equivalent. Okay. So you can have an inductor and you have a capacitor. So the inductor will have a j omega L impedance, capacitor will have 1 over j omega C impedance, and when they are equal, this becomes resonant. So you can have a certain resistance in the circuit too, but doesn't really matter. The part B, what is the electrical length of the resonator? So the electrical length of the resonator has to be, because this is used in an application where there's a transmission line and that length, and you have a inductor and a capacitor at the end. So that length it's asking, it's lambda by 4. So it's lambda by 4 at 1 gigahertz. So part C, we can't calculate it because we can calculate it if it's free space, but we don't know the coaxial lines electric constant or anything. So permittivity. So we just say lambda by 4 at 1 gigahertz. What is the impedance looking into the line at resonance? So at this resonance, if you're looking into here, if it's short and it's lambda by 4, this is open. So the impedance looking into here would be infinite. If the resonator is lambda by 4 longer, so if it's double that length, what is the input impedance at the resonator now? So instead of having a lambda by 4, now it's talking about even a longer line. That's actually lambda by 2. So if it's lambda by 2, so this becomes short, lambda by 4 becomes open, and then becomes short again after another lambda by 4. So this is actually short. That means 0 ohms is the impedance it will see. Okay, so now we've seen from the telegrapher's equations before that load and relationship. This is the relationship between input and the load. Something that I've done in a couple of slides before. When you calculate this parameter, when the length is lambda by 4. So if I do that again here, when the length equals lambda by 4, beta equals 2 pi over lambda, beta L becomes 2 pi over lambda times lambda by 4, pi by 2. So tan beta L infinity. So if I rearrange this term, take tan beta L out, get Z load over tan beta L plus JZ naught ZO over tan beta L plus JZL. Now because it's infinity, that cancels out, this becomes 0, this becomes 0. So I'm left with Z naught over times JZ naught over JZL. J cancels out. So I have Z naught squared equals Z in times Z load. So Z naught is Z in times Z load. Now this is important to understand the meaning out from this equation, because this tells you the impedance of this line. If we pick that impedance to be, if you know the load impedance, so for example, this is 50 ohm and this 200 ohms. Okay, so I can calculate my Z naught as 50 times 200 square root. So it will be easy if we had doesn't matter. So you get that square root of that value. Let's see, 100 ohms, right? So if you pick the impedance of that, so if this is 50 ohm, this is 200 ohm, and you pick this 100 ohm because that satisfies this condition, and this length is lambda by 4, that line will have minimum reflections towards the load because it transforms this impedance of 50 ohm to 200 ohm. So you have to use a line with 100 ohm impedance and a length of lambda by 4 to provide the transformation of impedance. So this is called the impedance transformer, and this is called the quarter wave transformer. So it's so this is a very important concept, and you'll notice that a lot of circuits will use that. And if you see a 50 ohm transmission line will have a certain width, and then you will see the 200 ohm delivered to the load will have a certain width, and then you'll notice there's quarter wave step transformers in most of the circuits, and that length is lambda by 4, and that width gives you 100 ohm. So this lecture only gives you outline of the concept. So you have to do a lot of reading, especially from the microwave and RF design systems approach book, Steer's book, because these all examples are taken from that, and this transmission line theory pretty much covers the chapter in the microwave and RF design book. So I suggest you guys read that, and then because you will get questions for exams from the examples that I'm doing. So pay particular attention and get things clarified. Now we'll move on to the microstrip lines. We were talking about transmission lines. So microstrip line is a form of transmission line. But when you want to calculate the impedance, characteristic impedance of a transmission line, there are empirical formulas, which is given by this. Now I said O1 then is given by this formula, which is dependent on the height and the width. So this is H and width, and then F1 is given by this formula. And then it has a dependence on epsilon effective, that's the effective permittivity, and epsilon effective is calculated by that, and these A and B parameters are calculated by that. So you'll notice that's a huge amount of calculations you need to do. I'm not going to ask you in this in the exam, but you will notice that just to find is it node, how many things you need to solve in empirical formula. So it's easier because it's an algebraic equation. So usually we tend to use some sort of calculator where we give only H, W, and then the epsilon R of the microstrip line, and the calculator will tell us what is the impedance of that line. So for example, this is a calculator that we use in AWR. So if you go, you can find this calculator in AWR under tools, and then you can pick what sort of transmission line that you want to look at. So it could be, microstrip line, strip line, CPW, as coplanar waveguide, coplanar waveguide, round coaxial slot lines. There's multiple things that you can insert the parameters, which is defined here, HW and epsilon, or the permittivity, thickness of the, so all those parameters, when you include that, and the substrate parameters. For 50 ohms, you can work out what is the width of the line that you need. So in your AWR project, KU band design, you are using microstrip lines, right? So the blocks like that, and say that input at the input port, you have a microstrip line of certain width, say, I don't know, 30 micrometers. So that 30 micrometers, if you include that in here and then work out, you'll get a certain impedance. So you need to make sure that whatever the width that you use is equal to 50 ohms, because your input impedance here is 50 ohms. Now what happens if you don't have at the input, if you have a different impedance, you get a reflection. That's what we learned in this course. So you need to make sure in your circuit, that's your amplifier LNA. So input impedance is 50 ohm because that's our reference, and the output impedance is 50 ohm. So whatever you present at this point here is also 50 ohm from the LNA. So that your reflection coefficient is Z load minus Z naught divided by Z load plus Z naught. 50 minus 50, it goes to 0. So you don't have any reflection back. And same way, you present 50 ohm to here from the LNA output, and then there's no reflection into the LNA, or if there's a signal that's coming from the output, some sort of, there's no reflection back to the load. So that's the whole point of finding the reflection coefficient. So what you need to understand at the end of the day is you need to match the impedance of the input to the whatever the input it sees afterwards. And in LNA you have two stages, say stage 1, stage 2, and then you have input, and then you have some sort of a matching circuit. Because stage 1 can be a transistor, and that input will have a certain impedance for that. Say it can be a complex number. So it could be, say, 20 plus 30J. I don't know whether it's right or wrong, but then your matching circuit will transform this 50 ohm to that impedance here. So what you need to have is something called conjugate matching. So the reflection impedance that you see here, this is not the reflection, that's the impedance. At this point should be said 1 star. So you can present, if you can somehow present 20 minus 30J, the imaginary parts cancels out. So it sees the real impedance here 20 versus real impedance here 20. And then it allows the power to transfer without minimum reflection. So a matching circuit when you design, so we'll talk about this a little bit more on Smith charts in the next couple of lectures. Its primary function is to transform this 50 ohm to an impedance from this 50 ohm to an impedance that's that much to here. So that circuit that you design could be cap and then an inductor and then a cap to ground. That circuit should do that for that particular frequency range. When I said frequency range, that's the band of interest. In your case, it's 12 to 16 gigahertz. That's in that particular band, it should transform this 50 ohm to the input impedance of the transistor. So that's the outcome of the all of this lecture. That's what we are trying to understand. So if you know each parameters, you can work out, the microstrip lines impedances, and when you have a set of elements, lumped elements, you can work out the impedance and then present the right impedance. So tune that so that it presents the right impedance to the input of the transistor. Thank you.